Tobias Freiding. Let's see what he calls it. Tobias will talk about our sensitivity analysis of the R-squared calculus.
Good afternoon, everyone. My name is Tobias, and I'm currently working on sensitivity analysis in linear causal models with a tool that I call the R-squared calculus. Okay, so suppose you have a very simple setup, a linear regression with some one-dimensional variable of interest, which we call D, and some outcome Y. And we also observe some other covariates X. And what we're actually interested in is the causal effect of D on Y. In a linear regression setup, that would just be the true regression coefficient. So if we then observe data from D, X, and Y, and we run our linear regression estimator, we get an estimate. But now the question is that estimate actually unbiased? Is it a good one? And to argue that we've actually estimated the causal quantity, we need an additional assumption. That is the assumption of no unmeasured confounders. And that means that we assume that there's no variable U outside of the system, which we did not observe, which simultaneously influences D and Y. So this is an assumption which we can't verify using data because we just don't observe U. So if you want to come around this problem, there's a more complicated setup called instrumental variables. And this, in principle, works even if we have an unmeasured confounder U. But we need something else. We need a variable Z, which we call an instrument. And this instrument Z, again, comes with assumptions. So it's not allowed to be dependent on the unmeasured confounder, and it's also not allowed to directly influence Y. And again, these assumptions are not verifiable. So this is a constant problem which practitioners have in practice, and this is the objective of sensitivity analysis, to explore this effect of unmeasured confounding. So onto the R-squared calculus. So suppose, again, we have a very similar linear regression setup. Then this quantity here, the R-squared value, or also called coefficient of determination, is the proportion of the variance in Y that our model can explain. So this quantity here is between 0 and 1, and it's 1 if our model can explain a lot, or if our model can explain everything, and it's 0 if it explains nothing. And we have a couple of calculation rules for these R-squared values, and these are, I think, the most important ones. The first one is just the definition, and we can also define a conditional kind of R-squared value. Very interestingly, in the case that Y and X are actually one-dimensional, the R-squared value is actually just the squared correlation between these two variables. And so we can also introduce an R value just by using the correlation. For this R value and the conditional version of it, we have this recursive formula, and we also introduce these two F values, which are just two transformations which we encounter a lot when doing computations with it. So that's why we introduced this abbreviation. So now let's see what the R-squared calculus can actually do for our problem. So this here is the equation of the outcome Y. We see our variable of instrument, then beta, which is the thing we actually want to estimate, and the effect of the unmeasured confounder and the effect of the measured confounders. So if we had the data for all of the variables here, we could consistently estimate beta. But since we cannot observe U, we need to fit the model without this quantity here. And this leads to a bias. And we can actually express this bias in terms of quantities in the R-squared calculus. Namely, it's just this formula here. So the fraction of the standard deviations here is no problem because we can estimate it. It only depends on quantities we observe. And these two things here are unknown. But the R-square calculus offers a way to interpret these in a very easy way. So for example, if a researcher believes that this inequality is true, which says that, okay, the effect of our unmeasured confounder on D is at most half times as strong as the effect of the measured confounders. Then we can apply a couple of calculation rules which drop out of the R-square calculus, and we can actually find a bound for this quantity here. And we can do the same for the first one as well. So this way we obtain a range for the bias that reflects the beliefs of a practitioner about his subject. So this was a very easy example with the linear regression. We also then did the same for instrumental variables, also for multiple ones. We considered this class of K-class estimators and maybe a mid to long-term questions also, whether we can put all of this in a computer algebra system. If you want to know more about this, please come visit my poster, and I'm happy to take questions.
Sorry. Could you give an example in this causal in this network, like give some real world correspondence, like I don't know, Y is a population, D is the height, whatever.
Sure. So for example, let's say this this Y is the wage, D is your education, and the unmeasured confounder is just ability. So we want to know what is the effect of education on your later wage. But this is confounded by ability, or by motivation rather, because a high motivation lets you both seek for good education, but also let you achieve a higher wage. So you want to exclude this variable here, but how do you measure motivation or ability or something like that? So what people came up with, for example, as an instrument here, would be proximity to a college. So the place where you grow up, the distance to the next university. So the argument is that the place where you grow up does not really affect your later wage. So that's the argument that this red arrow here doesn't exist. People also argue that the place where you were born is not correlated with your motivation or your ability. But again, you can also think about counter arguments in that case. So this really shows why sensitivity analysis is an important tool, because you don't need to justify that these assumptions hold precisely. You can put a number on it and say, okay, it might not quite hold, but maybe the correlation is only 10 or 20% or something. No.